Okay, so let's move on now to fundamental observation number 2. Fundamental observation number 2 is that the universe is expanding. And unlike the observation that the night sky is dark, which everyone has known forever, this is a discovery which is now perhaps about 100 years old, but is much more challenging to do. And the reason to that is that distances in astronomy are really hard to measure. And that's because, of course, you can't go there. So you can't take your meter rule and lie it end over end between here and the nearest star. You can just about go physically to solar system bodies, but beyond that it's much more difficult. And so distances become very tricky, and you have to use what's called the distance ladder to get them. I'm not going to go through the distance ladder in detail here, but the idea is that there are progressive rungs on this ladder. And you'll have seen some of these in kaleidoscopic astronomy, for example. But the idea here is that there are different progressive techniques which give you distances at different distance ranges. So, for example, within the solar system, you can bounce radar, or you can bounce light off other objects and see how long it takes to come back. That's quite a good way of measuring distances. You can also use parallax. That's the motion of stars on the sky as the Earth goes around the Sun, to actually get more distant objects, so stars within the galaxy. The most useful thing in general for cosmology is to use something called a standard candle. So and the idea of a standard candle, very simply, is that it's an object of known luminosity, and then when you measure its brightness, its flux, and you know the luminosity, you get the distance. And so the point here is, we've already seen, the flux that you measure is just L over 4 pi r squared. So therefore, R is just the square root of L over 4 pi f. And since I know L and I can measure f, I get the distance to this object. And so in cosmology, so examples of standard candles, and we will come back to these later in the course, are things like Cepheid variables and type 1a supernova. And they allow you to measure distances which are of order megaparsecs, hundreds to thousands of megaparsecs. And just to sort of give a handle on that, 1 megaparsec is about 3.08 times 10 to the 22 meters. So there's a reason we don't use meters. And a useful way of looking at how big a megaparsec is, it's approximately the distance from the Milky Way to Andromeda. So, for example, stars within the galaxy are perhaps typically about a parsec away, and galaxies within the universe are typically about a megaparsec away. And so, that's how you get distances to galaxies. If you find these standard candles in them, you measure the distance, and that gives you D. And that's hard. So distance is hard. On the other hand, velocity is easy. And what I mean by that is that if I take a picture or a spectrum of a galaxy, I take a galaxy and I split its light into its component parts, then what I see is something that looks a little bit like this. So I've got this bit down here, which is just what we call the continuum. This is basically all that's the light from the stars. But I also have these narrowed features here, and these aren't noise, these are what we call emission lines. And they have a known wavelength. And since they've got a known wavelength, if I take this galaxy and I give it some velocity kick, so I can have a positive velocity, and that gives me a redshift, or I can have a negative velocity, it's coming towards me, and that gives me a blue shift. So measuring the velocity is really just a matter of measuring the position of these emission lines of things like hydrogen, helium, oxygen, and things like that. So you can see these things that are written up here at the top just about, and they're what you need to measure. So you measure the positions of lines, and in principle they don't just have to be emission lines, you can also get lines in absorption. It's just that these emission lines are easy to see. So absorption lines go down, emission lines go up. And then you just use the Doppler effect. And for low velocities, of course, that just tells you that the wavelength you observe over the rest frame wavelength is equal to 1 plus v over c. And we make that equal to 1 plus z, where z here is a quantity we're going to call the redshift. And just to sort of give you a little note as an aside, you know, the most distant galaxies that we know have a redshift of about 10. Of course, that doesn't mean that they're going at 10 times the speed of light. It's that effectively what you have to do is you have to use, you know, this is a non-relativistic formula. We tend to use a relativistic formula. You know, it's 1 plus v over c plus, or multiplied by, the relativistic correction. But the point is, we still call all of that quantity 1 plus z. So we are allowing the redshift to be large, much larger than 1. And that does not imply superluminal motion. And what you can then do is you can plot distance versus velocity. And what does that give me? That gives me a diagram that looks something like this, and you'll notice firstly it is a linear relation, and it has the following form: V equals H naught D. So it goes through the origin, and it has some slope, and the slope is what we call the Hubble constant. And so this equation here is called the Hubble law, or sometimes now the Hubble-Lemaitre law. And H naught is the proportionality constant. and we call that the Hubble constant. And just a sort of little note, because this will come back later, the 0 subscript means at the current time. So the Hubble constant is not necessarily a constant for all time, it's something that you measure now. There is also a more general Hubble parameter. But throughout this course you will see things given with a subscript 0, which always means at the current time. And there's a big implication of this, and the implication is that more distant objects recede more rapidly. Yeah, and that's a fairly significant implication. If things that are further away from us go faster, then firstly it tells us that we have another way of measuring distance, but also it tells us that the universe is expanding.